organizer of the MLRS. Professor Chih-Jen is distinguished professor of computer science from National Taiwan University. He is a leading researcher in many subfields of machine learning and optimization in particular. And he received his PhD from University of Michigan in 1998. And he has made a lot of significant contributions to machine learning, both in the form of fundamental understanding and practical tools. So you might have heard of libSVM or liblinear, like blazingly fast SVM implementation. If you haven't tried, please do so. And Professor Chih-Jen received a number of awards and honors, including ACM Fellow, AAAI Fellow, IEEE Fellow, and other awards, including 2 Best Paper awards that I'm aware of. So without further ado, please welcome Professor Chih-Jen.
Thank you. So first, I would like to thank the organizers for inviting me here. I also want to thank my old friend in Michigan for arranging the trip and inviting me here. So this is the first talk in the summer school. So we are going to give an introduction. But this morning, when the program chair talked about the statistics, I saw that we even have high school students here. So that makes the background of our audience very, very diverse. Because I think, so originally the summer school, the goal was to introduce the research trend for, I think, graduate students. But as you can see, so I still remember that more than almost 20 years ago in Taipei, we had a very huge machine learning summer school. I remember at that time we had 1,000 attendees. That may be the largest machine learning summer school ever. At that time, we didn't have any high school students, and I think we had very few undergraduate students. But you can see that things do change. Now AI is an area that everybody wants to do. So that's the part that has been changed, because now AI is everywhere, machine learning is everywhere. But on the other hand, some basic materials, they are still the same. We still need to learn those things. Therefore, the design of my talk is more for like, I think maybe suitable for final year undergraduate students or first year master students, to introduce them some basic concepts of empirical risk minimization, and also introduce optimization techniques. But now when I mean optimization techniques, I'm talking about optimization methods for deep learning. Yeah, not the traditional optimization methods. So that's about this course. And I want to say a few things. So my main job is a professor at National Taiwan University. But on this page, you also see another logo, because I'm also an affiliated professor at this MBZ UAI at Abu Dhabi, UAE. This is a new university. They claim that this is the first AI university in the world. So they are in Middle East. They put lots of efforts in developing artificial intelligence for both research and applications. And we are recruiting students there. They provide good support for both master and PhD students. So even for master students, they give full support. And right now they are getting good students. Therefore, if you are interested in graduate studies, you can consider this university and try to check more information. Now go to the real materials. So here are the outline. First, I will have introduction. Then I want to give basic concepts of empirical risk minimization. I will start from something very simple. That's linear classification. From that, we talk about the simplest neural networks, and then the more complicated ones. Now deep learning is popular, but behind that, we need to solve an optimization problem. Therefore, the second part of my course will be on stochastic gradient methods. Let's start from the basic thing. So what is machine learning? So traditionally, when we say machine learning, we mean that we want to extract knowledge from data. Usually, we say there are two types of machine learning tasks. One is the classification, and the other is clustering. That's the traditional way to categorize machine learning tasks. So what's the difference? The difference is that for classification, you have some so-called labeled data. Now for the figure on the left, you have circles and triangles. So circle and the triangles, they are the so-called label information. And we collect some features. So here, X and the Y axis, they represent certain features. From those labeled data, we would like to learn a model. In this example, the model means this dashed line. Once you have built this dashed line, then for any new data point, as long as you have the feature values, then you can check if it is on the right or on the left of the model. Then you can predict the label of that instance. That's for classification. Then in the right figure, clustering means you don't have any label information. Now we have probably maybe 13 points in this figure. Then there are several ways to cluster them. From the geometrical relationship of those points, you can probably say that we have 3 groups. So in that sense, you cluster all the points to 3 groups. But on the other hand, you can say that each individual point is a cluster. Or alternatively, you can put all data points in just one cluster. Therefore, the main difference from classification is that now we don't have label information. But in my talk, I'm going to focus only on classification. I'm not going to talk about clustering. And I have already said that for the task of classification, now from data with labels, we are going to build a model for future prediction. And here's another, here I show more details about data classification. So that means we are given training data in different classes. And for training data sets, that means for each data instance, we know their label. Then we build a model for prediction. Then in the prediction stage, the labels are actually unknown. So here's a classic example. Suppose you want to build a machine learning tool for medical diagnosis. Here is what you can do. For every patient, you can measure the blood pressure, height, weight of this patient. Each such value is called a feature value. But what is the label? The label means whether the patient eventually recovers or not. But how do you know the result? In general, getting the label information is difficult. So what you can do is that you just wait for several years. Then you know if this patient recovers or not. So you can see that this is an expensive process to get the label information. So now you have label as well as feature values. Then we can build a machine learning model. After that, this model can help medical doctors to do prediction. That means for any new patient, what you can do is you also measure the blood pressure, height, weight of this new patient. You put those feature values into the model, then you can predict if this patient will recover or not. So that's a very basic idea of how classification works. Therefore, usually, we say there are two main stages. One is for training. From the given labeled data, you try to build a model. After that, you deploy your model for prediction. But then the question is, how to build a model? There are several ways. In classification, or say in traditional supervised learning, there are many classification methods. So for example, you can build a decision tree, or you can do something else. But quite a few classification methods, they can be under the umbrella of empirical risk minimization, including deep neural networks. So that's what we are going to talk about. So now our task is to build a model. But then the question is how to do that. Then a very intuitive idea in building a model is by saying this. How about finding a model so that the number of training errors is minimized? Therefore, now we have an optimization problem. The variable of the optimization problem is the different possible models. You want to choose a model so that under this model, the number of training errors is minimized. So that means all or most training data with labels, they should be correctly classified by our model. So here, model can be anything. So for example, if you do a random guess, and also for this data set, training data set, 50% are positive, 50% are negative. So the percentage of training error is going to be 50%, right? But, so this is not very good. But anyway, that's one consideration. So random guess is already a model. That's among our consideration in this minimization problem. But the difference is just that. Now, we are hoping that our training error can be as small as possible. But we can have many choices of the model. So for example, you can consider a decision tree, a neural network, or many other things. But this idea of minimizing the training errors is called empirical risk minimization. We are hoping to build a model so that this model can correctly separate our labeled data. But now we want to discuss more about finding a good model. So for simplicity, let's consider that the model to be a vector W. So why a vector W can be used as a model? The reason is that if now you have such a vector, then your decision function can be just by doing the inner product between your model vector and your test point. So this W is your model, and X is the feature vector of a test instance. What we do is just the inner product. After the inner product, you get a value. Then you check if this value is positive or negative. Then you can predict this point X is in which class. So now we understand that this vector W can be a model for consideration. And I have already said that we simply check if the resulting value after the inner product is positive or not. If it is positive, then our predicted label is this positive one. Otherwise, we predict that this X is in the negative class. So in a two-dimensional situation, the model is simply like a straight line passing through the 0 point. Because we check if this W transpose X is positive or not, right? So in a two-dimensional space, then this W is a two-dimensional vector. Then our model is simply like this dashed line. Now the equation of this dashed line can be represented by this W transpose X equals 0. Then for any new point X, after the inner product, we check if this value is positive or negative. So now you have a question. Why we are using a quite restricted way as our model? Now you can see that our model is simply a dashed line passing through the 0 point. It's very restricted, right? What if all our training points, say circles and triangles, are in this area? Then you can never use a straight line passing through the 0 point to separate them. For the figure I showed, this is a good example. I can use this dashed line to separate the two groups of data, but that may not be the case if we say we move those triangles to the upper part of the figure. Therefore, you may argue that this is a very restricted way. But in practice, we may be fine. The reason is that usually you have a lot more features. Then that means you are trying to have a so-called hyperplane in a very, very high-dimensional space, even though you require that hyperplane to pass through the 0 point, then it is still capable to separate training data in most situations. Therefore, right now in our discussion, we just consider things passing through the 0 point. Of course, there are other ways. There are ways to not require your model to pass through the 0 point. But let's not worry about that for now. So what's next? Now we are assuming that the model is a vector, but we haven't said what this vector W is. And indeed, we need to find out this W vector. So we don't know yet how to find this vector W. But a question now is, if you already have W, then that means you already have the model. You need a way to characterize the number of training errors. That means, suppose now W is given, then we need a way to check that under this W, how many training points are wrongly classified. So that's what we mean, a way to measure the number of training errors. So I have said that we need to characterize the number of training errors. To do that, in machine learning, usually we use a so-called loss function. So what does a loss function do? For this function, there are two types of input. The first is our model. The second part is a data instance. Essentially, we want to check if this data instance is correctly predicted by our model. So for the given instance, this given instance comes with feature values as well as labels. Why? Because this is training point. For training point, we do have the label information. And right now, I'm considering binary classification. That means I only assume that things are in two classes. Therefore, now for notation, I assume that for every test instance, it's a pair of label y and the feature vectors x. So here, y is a value of plus or minus 1 to indicate the class information. And x is the feature vector. So in my slides, for vectors, they are bold-faced. So you can see that this x is a vector, but y is a scalar. And it is a spatial scalar. It is either plus or minus 1. So for the given model and the given training instance, we use a loss function to characterize the training error. The simplest way is to have a 0-1 function. That means to count the number of training errors. So this is one way. This is called 0-1 training loss. The definition is as follows. So the model W is given, and for the training feature vector X, we can do the inner product, this W transpose X. So suppose this W transpose X is positive, then we are hoping that the corresponding Y is also positive. That means our prediction on this training point is the same as the true label. Therefore, this Y and the W transpose X, they should have the same sign. But if unfortunately they have different signs, then that means this is a wrong prediction. Say for example, if Y is positive, but W transpose X is negative, then a positive value times a negative value is less than 0. Now we know that for X, our prediction is wrong. So this is a training error. Therefore, the output function of our loss function should be 1. That means we count this as one error. But otherwise, if Y and the W transpose X, they have the same sign, then we say this is a correct prediction. Therefore, the number of error is 0. So now, this is called the 0-1 training loss. The output of the loss function has only two possible values, either 1 or 0. So this function looks good. We have a way to count among the training points, there are how many errors. However, this function is discontinuous. And this can be an issue later when we want to solve the optimization problem for finding this W vector. Let's see why this function is discontinuous. Let's draw such a figure. For the x-axis, we show the value of minus y W transpose X. We are hoping that Y and the W transpose X to have the same sign, right? Therefore, if the prediction is correct, Y times W transpose X is positive. And then take the negative, we get a negative value. That's on the left-hand side. That's the situation of a correct prediction. Therefore, the value should be 0. But on the other hand, if our prediction is wrong, then Y times W transpose X is negative. Then taking the negative sign here, we get a positive value. Then the loss function has the value 1 to indicate that we have one training error. Therefore, this is the figure of this 0, 1 loss function. Clearly, it is not continuous at this 0 point. Suddenly, we jump from the 0 value to the value 1. This is an issue because later, in solving an optimization problem for finding W, due to this discontinuous situation, then we might have problems to identify a good W. And also, this is not a so-called convex function. But anyway, we don't like such a figure. So we are hoping to have some other ways to characterize the training loss. So people usually consider continuous approximations of this 0, 1 function. So here are two examples. They are the common loss functions that people are using. It's easier to look at the figure. In this figure, the y-axis is still the value of the loss function. And also, for the x-axis, I still have minus y w transpose x. And you remember that in this place, we have such a 0, 1 function. But now we do something else. We still have values to be 0 or close to 0. But we don't like that jump to the value 1. Instead, we consider an increasing function so that on the right-hand side, this loss function value keeps increasing. This is reasonable. One interpretation is saying that if this minus yw transpose x value is very large, that means your prediction is totally wrong. Therefore, you put a large value as your loss. That's one interpretation. And simultaneously, because of using such an increasing function, then we get the continuity. So now we have a continuous function as our loss. But this is a figure to show the idea. But mathematically, we can represent them in certain expressions. Let's consider the first one. This loss function has a name. It is called the hinge loss, or sometimes called L1 loss in machine learning. It is the value of to take the max between 0 and 1 minus yw transpose x. So let's check details. Suppose your prediction is correct. So this yw transpose x is positive. And 1 minus a positive value, then it goes to negative, right? Taking the max with 0, then the value is still 0. So that's the situation on the left. You get the value 0. But on the other hand, if your prediction is wrong, then this yw transpose x is negative. 1 minus a negative value becomes positive. Doing the max with 0, you get a positive value. So that indicates you have a training error. So this explains this hinge loss. Let's check another popular loss function. That's the logistic loss. This is the mathematical form. We have this log of 1 plus exponential minus yw transpose x. Now let's see. If your prediction is very good, is right, then yw transpose x is positive. Exponential minus positive value, that is very close to 0, right? So now this value is very close to 0, but we know log 1 is 0, because now we have 1 plus a small positive value. So this value is very close to 0. That's the situation here. Because you have the log function, so the value never really goes to 0, but this is very, very close to 0. But on the other hand, if your prediction is wrong, that means YW transpose X is negative. Then minus a negative value is actually very large. Is a positive value. Then exponential, this positive value is going to be a huge value. And if you ignore this value 1, log and exponential are canceled out, then you actually get YW transpose X. So that explains why, for this logistic loss, after values become large, you get almost a linear function. And this linear function keeps increasing. And that tells us that the error is pretty large. Therefore, now we have shown that those two expressions, they are reasonable way to characterize the training losses. And turns out that such two loss functions, they correspond to two important classification techniques in machine learning. For the first one, if you use such a loss function in order to identify your W vector, then that's actually the linear support vector machines. So for linear support vector machines, it considers this hinge loss. On the other hand, if you consider this logistic loss to find the vector W, then the classification technique is called logistic regression. So both are very classic supervised learning techniques. As I said here, they are very fundamental methods. And also, from the way we introduce them, you can see that the two methods, their performance should be similar. Therefore, if you see a paper, they report the performance of linear SVM and the logistic regression. And this is not, and also the problems are reasonable and the typical ones, but they report very different test accuracy, then very likely something was wrong about their settings. Yeah. But here I'm talking about linear. Kernel is another thing. Because if you consider kernel support vector machines and the linear logistic regression, well, that's a different thing. But for logistic regression, you can also do kernel. That means kernel logistic regression. So now looks good. We have a way to characterize the training losses. Then it seems that we are ready to solve an optimization problem. However, in machine learning, we need to have an important concept that minimizing the training error may not give you a model for future prediction. The reason is that overfitting may happen. I'm going to give an illustration. But here, let's say first, in supervised learning, getting 100% training accuracy is in some sense useless. So why? Because for training data, you already have the answers. So those answers are your prediction. So you already have 100% training accuracy without any machine learning knowledge. Because your data, you have answers. But the issue is, you are going to deploy your model to a real environment for prediction. In that real environment, you don't know the answers. Right? And what you hope is in that prediction stage, your performance is good. So in building a model for classification, then you should do two things. One is to avoid something called underfitting. So underfitting means you do not learn enough from your data. But how do you learn enough from your data? That means you hope that the training error is small. That's the way to avoid underfitting. However, as I said, getting 100% training accuracy, or say 0% training error, does not mean that you get good performance in the future. We need to avoid something called overfitting. So here, overfitting means you overfit your labeled data. Then you get a very small training error, but somehow in the future, when you do prediction, your test error may not be small. So here I give an illustration. The left-hand side shows training points. So for those solid circles and triangles, I have training points. And our job is to build a machine learning model. And now we know that our model is a line. Suppose that we consider such a line. So why considering such a line? The reason is, you see a triangle here, right? But now we are hoping that our model can correctly separate the two classes of data. And in order to handle this triangle, we have no choice but to consider such a dashed line. And in machine learning, this means we are trying to fit the training points. And those training points, remember, we have label information. But is this a good choice? Probably not. For the figure on the lower left, I have the same training points, but instead of the dashed line considered earlier, now I consider another one. We argue that this one may be better. So why? The reason is that this triangle may be a wrongly labeled data point. This is very possible in a practical environment, right? So in a real world environment, you need to collect data, and therefore, easily you made mistakes. So some instances may be wrongly labeled. Then originally, we want to fit data, then we consider such a model. But if we suspect that this triangle is wrongly labeled, but why we suspect that? Because we have seen other points. So roughly speaking, we can see that circles, they are in such an area. They are distributed in such a way. And the triangles, they are all in this area. And because of that, we think such a line might be better for future prediction. And now for figures on the right, I show some test points. As we can see, circles, they are roughly in the same region as those training circles. And also triangles, they are roughly in the same area of the training triangles. If we use this line, then you can see that circles in this place or triangles in this place, they are wrongly predicted. However, if we use this one, then, well, here I show perfect. Well, of course, this is an artificial example. But as an illustration, what I want to tell you is that your training data, the label information may be wrong. You may not always need to fit the training points. Instead, what you want is a model that generally captures the distribution of training data. That should give you better predictability in the future. So that gives us the idea that a good machine learning model, first, you need to learn enough so you avoid underfitting, but you don't want to overfit training points. But then the question is how to do that. In machine learning, an important concept to avoid overfitting is called regularization. What's the idea? First, we recognize that in minimizing the training error, we may go to manipulate our W vector in order to fit the data, such as this example. Now you can see that we try to bend this dashed line in a way so that we can fit the training points. So mathematically, one concept to avoid overfitting is to say, can we have a way to avoid that W vectors are not that extreme? So say it again. We want a way to make values in W to be less extreme. One idea is to make those W values to be close to 0. But mathematically, how to do that? Well, we can add now the so-called regularization function into the training error function that originally we intend to minimize. But why such a function? The reason of considering such a function is because if you go to do the minimization of this quadratic function W transpose W, then what's the solution? The solution is 0. Minimizing such a quadratic function, the minima is 0. Or if you consider just the one norm of the vector W, the minima also happens at the 0 point. So we know that if we go to minimize such functions, then it is possible that we make W values to be less, to be closer to 0. And that may be one way to avoid overfitting the training points. Well, this is the idea. We're not very, I'm not talking about strong theoretical support about doing that. So now we can write down the optimization problem for linear classification. So this is a formal definition about linear classification. Here for the notation, I assume that I have a training set, including L training points. And I have index I is from 1 to L. And each I corresponds to one training instance. So an instance is a pair of label and a feature vector. So yi is either plus or minus 1 to indicate the true class label of the data point I. And this xi, now an n-dimensional space, n-dimensional vector, that's our feature vector. So I use L to represent the number of data and N for the number of features. Then we are going to solve an optimization problem, this to minimize a function f of w. And this f of w is defined to be a combination of two things. The second term is actually the summation of training losses. So remember that we already have a loss function to characterize the training loss on each data point. So for data instance yi, xi, with the given w, I have a way to measure the training error. But I need to go over all the training points. Therefore, I do a summation. So here I have summation over all the L data points. Therefore, originally, we are supposed to only minimize this summation. We want to identify W so that the sum of training losses is minimized. That's the original thinking, to minimize the training error. However, we have mentioned that the overfitting may occur. Therefore, you don't get a good model for prediction. Therefore, people say that, how about adding the regularization term into the function to be minimized? And earlier, I mentioned that there are several possibilities. Let's consider now this quadratic function as our regularization term. So it's like now we have two objectives. One is to minimize the total training loss. The other is to minimize the regularization term. Of course, in optimization, you can do something called multi-objective minimization, but that is a little bit complicated. So in machine learning, what people do is to say, okay, how about let's combine the two terms. Now you can see that in this function f of w, we do the summation of the two terms. Such a summation becomes the function to be minimized. Then we minimize this function over all possible vector w. And suppose we are able to solve this optimization problem, then we get this optimal vector w, and we are hoping that this one can give you, can be good in future prediction. But then there's an issue. How do you do the combination between the regularization term and the training loss? But the answer is actually we don't quite know. So those machine learning researchers, when there's something they don't know, then they just say, okay, let's leave the job to our users. So what they simply did is they do a combination, but they put a weight vector here. So here this C is the regularization, is the so-called regularization parameter. That means you adjust the importance between the two terms. Okay, thank you. This is quick. So if you consider that training errors are very important, then you want to enlarge this, this value here. So the second term becomes more important. Then that means you try the best to minimize the training error. But now if you really worry about overfitting, then you put this parameter to be very small. Then regularization term becomes important. So now in machine learning, this kind of parameter is usually called hyperparameter. In machine learning, people call this W parameters. So we minimize a function in order to generate parameters So then we get the model. But beyond the parameters, there's a hyperparameter that we need to decide. This is usually a very complicated thing about deciding the hyperparameters. The reason why now those people use those GPU clusters and to waste lots of energy, I think very often is on tuning the hyperparameters. So that's still a very important research topic we need to do. So now I have introduced the basic formulation of linear classification. Now I will move to neural networks. What I'm going to show is that for neural networks, we are able to use the same way to describe our optimization problem. But now for introducing neural networks, I would like to extend our setting from binary classification to multi-class classification. Well, the reason is that if you have a network, very easy, you can handle a multi-class situation. Therefore, now in my training set, I still have L training points. However, each data point, each training instance now has yi and xi. So xi is still the feature vector, but now yi indicates the labels, right? But this yi is also a vector. So earlier, this y is plus or minus 1. It is a scalar. But now I have this yi, also a vector. I call this a label vector. So why I need a vector? Because I need a so-called indicator vector to indicate the class of this data point I. Because I no longer have only 2 classes, I have more. I assume that I do have k classes. So here this capital K is the number of classes. Then for data point I, it is in one of the k classes, right? So this yi is a 0, 1 vector. So that basically all the points, all the components are zeros, except one component is 1. This component 1 indicates the class of the data point data point xi. Say for example, if xi is in class this small k, then in this yi vector, I have all values to be 0, except that at the k's position, I have the value 1. For such a vector, we call this an indicator vector. Because only one element is 1, and from the position of this value 1, that's also the index of the value 1, then we know the corresponding class label. Therefore, now I have a label vector, and such pairs of yi, xi, they are elements of my training set. Then the idea of a neural network is to map each feature vector to one of the class label by the connection of nodes. So here is an example. Here A1, B1, C1, well, they are like you have 3 features. For every data instance, I have 3 features. And I use certain weights to connect things from the first layer to the second layer. So I use those weights to do some calculation to generate values, or so-called intermediate values. That's the second layer. I can continue to do that for several layers. And in the end, and here, I actually assume that my data set are in 3 classes. Therefore, I have 3 nodes here. And I'm going to use the output values to predict that the input instance is in which class. That's the idea of a neural network. But then a big issue is why such a network is useful. There are many interpretations. People may say that this is probably related to how the human brain works, even though I don't really know. But one interpretation is this. Linear classifier is actually the simplest neural network, just 2 layers. For the linear classifier that we just talked about, we actually have the simplest neural network. The input layer includes our features. Then immediately we have an output layer to indicate class labels. So if linear classifier works, how about extending that to multiple layers? Probably you get better results, right? That's one interpretation. But now that, anyway, let's assume that using multiple layers may work. Then let's discuss how to generate such a network. But to do that, we need to consider operations between 2 layers. So now, between 2 layers, I'm going to use a weight matrix to map input. So input means results from the previous layer to our current output. So the output of the current layer is going to be the input of the next layer. Mathematically, that means I'm going to use a weight matrix Wm at layer M for the mapping. So you can see that I still use the symbol W. This symbol W is actually very similar to the vector W I used earlier. But earlier for linear classification, I only need a vector W. Well, because I'm considering binary classification. But in neural networks, this is more general. So I need a matrix. But the role of this weight matrix W here is the same as the vector W earlier in linear classification. Now this W is responsible for doing the calculation with the input information to generate the output. So say it again. Now you have the input value, right? That's like our features. From input feature values, we are going to use this W to generate the output. But you remember earlier in the linear classification, all I need is one weight vector called W. But now I need a symbol M here to indicate that this Wm includes parameters for the layer M, because now I have multiple layers. And the size of this matrix is going to be Nm plus 1 times Nm. What is Nm? Nm is the number of features at the current layer. That means the number of input features for the current layer. Then nm plus 1, that means the number of output features at the current layer. And this is going to be the number of input features at the next layer. And I assume that in my whole network, I have this capital L to indicate the number of total layers. Then we need to define the operation from the original input to the final output. Under my definition of nm and nm plus 1, now you can see that this n1 is going to be the same as the number of features of the original input instance. Therefore, from the given training points, you have a feature vector, right? Then the dimensionality of this feature vector is going to be our n1, because that's the input size of the first layer. And remember, we have this capital L to indicate the number of layers. Therefore, this NL plus 1 is going to be the same as the number of classes. Those are clear. Then we need to define the operation between two layers. Now let's assume that this Zm is the input of the current layer M. And of course, when M is 1, the input of the layer 1 should be the original input vector x, right? Therefore, Z1 should be the data point x, this feature vector. Then from Z1, we go to generate Z2, Z3, etc. Until the last layer, we have this ZL plus 1. That's the output of the whole network. And this output of the whole network should be able to predict the class label. So that's the idea. Then we need to specifically define the operation from the input to the output. Here is what we do. From the given input, this Zm, we do a matrix vector product. This Wm times Zm. Then we generate a vector called S. Now you can see why. Earlier in defining this Wm, the size of the matrix should be Nm plus 1 times Nm. So this Nm is the input size. Only if that's the case, we can do the matrix vector product with the input vector. So what we do is, we do this matrix vector product, then we generate one vector. I call this S. So looks like now we can directly use S as our output for the next layer, right? But there are some issues. I will talk about that. So that we cannot just directly use S. Instead, we need to put S into a nonlinear function. Now in deep learning, usually this is called the activation function. Usually, this activation function is a very simple function. Here, I mainly consider a simple scalar function, even though you can consider more complicated ones. But if you consider a very simple scalar function, then for every component, the j component of the vector S, I put that scalar into the activation function. Then I call this the output, the component J of Zn plus 1. After going through all the components, I generate the vector Zn plus 1. That becomes the output of the current layer. And the output of the current layer becomes the input of the next layer. That's the idea. But usually, people, besides using the W, people also do a bias term. So a bias term is another vector of parameters, so that the way we generate S is by W times Z plus B. So what's the role of the bias term? If we go back to the linear classification situation, you remember that in a figure, we criticize that we require our model to go through the 0 point. But it is easy to generalize that by adding another parameter B. So if you have W transpose X plus B equals 0 here, then your straight line doesn't need to go through the 0 point. People often call this a bias term. A question is that, do we always need the bias term? The answer is sometimes you need, but sometimes it doesn't matter. As I said, like in the case of linear classification, if your number of features is large enough, is high dimensional enough, then you don't really need a bias term. But anyway, following the convention of people using neural networks, let's consider such a bias term. Therefore, now the way to generate S is from Z. We do the matrix vector product plus a vector B, so we generate S. I have mentioned that the activation function is usually a very simple scalar function, and this one does a nonlinear transformation. There are various reasons of using this activation function here, but here, let me discuss a very important reason why we need an activation function. Suppose you don't have an activation function in your neural networks. Then what we get is something like this. Well, now also let's assume that there is no bias term. Then what we have is this. Well, in the beginning, we have X. That X is also our Z1, the input of the first layer. Then we do this W1 times Z1. Then we generate Z2. Then Z2, we also do matrix vector product with W2. Until the end, we generate WL as our output. And this is a case without any activation function. Then what happens if we don't use an activation function? Your output is going to be the product of all those matrices times your input vector. And there's totally no need to have those different weight matrices. All you need is just to check what's my output size, what's my input size. You only need one weight matrix W. Yeah. The reason is because the product of those matrices becomes one single matrix. What does this mean? This means we end up with having only a linear mapping from the input to the output. Then we go back to linear classification. But the reason we are doing neural networks is we hope to do something beyond linear classification. So we need to introduce some nonlinearity. Therefore, after W, we have an intermediate vector S. Then we put this S into a nonlinear function to generate our output. That's the reason of having an activation function. Now I would like to make a connection between neural networks and the original optimization problem of linear classification. In order to build the model, we need to identify values of those weight matrix, right? You remember earlier in linear classification, we solved an optimization problem. And what is the variable of our optimization problem? The variable is the vector W. The situation is similar here. All those weights between two layers, they are variables of our optimization problem. We need to decide those weights, because once you have those weights, then you are able to do prediction. That means you already have a model. Now let's do one thing, is to collect all our variables. At the layer 1, I have this matrix W1. But this W1 is a huge matrix, but I can vectorize it, say like by concatenate all the columns of W1. Then I get a vector. So this vector operation of W1 can generate a long vector. You convert this matrix to a long vector. At the layer 1, we originally already have a bias vector B1. Then we do the same thing for the second layer until the last layer. Then we are going to have a huge vector variable, right? Now I use theta to represent the collection of all variables. And this theta, I say this is n-dimensional vector. But why I use n? Because n, back in linear classification, that's the number of input features, also the size of the vector W. That's the number of components in our model. So here, I intend to use the same symbol. This n indicates the number of variables, or say the number of parameters in my network. This is going to be large. The size, this n is going to be this summation. Because for W1, then the number of components is actually n1 times n2. But I have n1 plus 1 here because I need to consider the bias vector as well. And then plus until the last layer. This value becomes the total number of variables in solving the optimization problem. Then we are going to have the following optimization issue in training a neural networks. I still use the same f of theta to indicate the function I'm going to minimize. And you can see that I minimize f of theta over this variable vector theta. That means I'm going to adjust the weights of the neural networks to see which one gives us, say, the smallest number of training errors. Then this f of theta is defined in this way. Now this is quite familiar to you, right? Because in linear classification, we already have the summation of two terms. In fact, we have the same thing here. we still have the regularization term, because for neural networks, we also want to avoid overfitting. But we want to learn enough from the training points. Therefore, we have the summation of training losses here. And you remember this regularization parameter. This is something we don't know how to adjust between the two terms. So this is decided by users. So the important thing is about this summation. Now the formulation is very similar to the linear classification. But what's the main difference? The main difference is that this loss function now becomes a lot more complicated. We still have the input training instance xi, so the feature vector, and the yi, the class label vector. Then from the given xi and the yi, suppose theta is given. That means the network is decided. Then we can input xi, yi, and input xi into the network to generate the final output vector. Then we can compare the final output vector with the true label vector yi to get our training error. And then once you have a way to characterize the training error, you do the summation. So the concept is exactly the same as doing linear classification. So the important thing is to get the output vector. Once you have an output vector, then there are various ways to define the loss function. You can generalize, for example, the logistic loss for this multi-class scenario. But here, let's consider a very simple regression function. You remember that our yi is an indicator vector. That's a vector of 0, 1. Now, of course, we are hoping that our output vector z is very close to the 0, 1 vector. Therefore, we can minimize their difference. But we like square function. Therefore, after minimization, we take the square. So such a squared function can be our loss function. Therefore, now we see that the formulation is the same as linear classification. However, the loss function is a lot more complicated than linear classification. But anyway, what we have shown is that for the linear classification, from linear classification to neural networks, they are under the same concept of empirical risk minimization. Yeah, that's the message. And now we have seen that when using neural networks, the loss function involving this network structure, therefore, it is, of course, more complicated. And then, because of that, the function is no longer convex. Back to the case of logistic regression or linear support vector machines. This loss function is convex in is convex in the variable w. But now we don't have that. So even though here we use this squared loss function, the squared loss function is convex in this ZL plus 1. But theta is our true variable. Because when we say convexity, we are talking about from the viewpoint of theta. This theta includes all the weights from in different layers. Therefore, this is not a convex function in theta. So that makes neural networks training more complicated. And the things are even more complicated because earlier in this discussion, I'm considering one single instance from the input x, then I do the matrix vector product until I find the output vector. But in doing the training, I have many training points. So I have I from 1 to L. Therefore, for every instance I need to go through this procedure. But this makes the training process more complicated. Okay, for the session before the lunch break, I still have 5 minutes left. Yeah. Well, let's continue a little bit. I assume that you are not hungry yet. So I've been a teacher for many years. One thing students tell me is that you never teach you never teach more than the scheduled time. Students will complain. So I promise I will stop in 4 or 5 minutes. Yeah. But the issue is that I am not. I won't have enough time to finish this. Finish introducing convolutional neural networks. The reason is I want to spend enough time for the second part, is to introduce stochastic gradient methods. So I need to decide how that certain things are must be omitted. But anyway, these convolutional neural networks are now very well known for, say, image classification. So we want to get an idea how from the simplest, these fully connected neural networks, we can do something else. Yeah. That's the idea we hope to let you know. I think the setting is the same. We still have a K-class classification problem. Now assume that we still do multi-class classification. So every data instance is in one of the K classes. The one important difference from convolutional neural networks and the original fully connected networks is that we already assume that the input is somehow a kind of images. Therefore, for the input of the first layer, now instead of like xi or something, I directly use called z1i. But okay, this I is for the data for the instance index. So let's not worry about that. But this value, this index 1 means the first layer. So this means the input. But use a capital letter to represent a matrix. So an image is a two-dimensional thing, right? So we need a matrix. So in terms of notation, that's the main difference. And this vector y is the same, still have an indicator vector. For convolutional neural networks, the idea is the same. From the input image, we want to do a mapping from layer 1 to layer 2 until we get the output vector. And we hope the output vector is very close to the label vector. Therefore, things are very similar. But then the question is how to go from one layer to the next. I think we need to stop here because this is a bit more complicated. So see you in the afternoon.